DAG, longest path in a DAG. From where we have to start?
Sir,
Hmm, I'm not able to hear you. Okay, let's wait for some more time. Let other people join and then we'll start. So, okay. So from which point we have to start? Can somebody, because I was not able to hear you, like whoever was speaking earlier, I was not able to. So is my voice audible to you?
yes, sir.
Okay. Is it clear, right? It's clear.
Yes,
So for is topological sorting done?
yes, sir.
Okay. DAG we have discussed already. So
Yes, sir. DAG we have discussed.
okay. So we have to start from longest path in a DAG, right?
Yes.
Okay. So we'll start from there. Or shall we wait for some more time because very less people are joined? What should we do?
Sir, we can wait. We can wait.
Okay, let's wait for some more time. Maybe we'll start by 17. So we'll wait for 3 more minutes and then start. So let's start. Maybe we can watch it later. Are you able to see my screen?
Sir.
Yes, sir.
Okay. So let's start with the topic. First, we'll cover what. So you already told the topological sorting is done. Okay, so let's start. Okay, so you are aware of DAG, right? What are the basic properties of DAG?
It is directed and acyclic.
Do you have any cycle in DAG?
No, sir.
No, right? Okay, so in the DAG, the basic properties is what? There must be one vertices, vertex, sorry, with in degree
Zero.
equals
Yes.
to 0, right?
Yes.
In degree, you are aware of that, right? In degree, what is
Yes,
in degree?
sir. Number of nodes which are coming to a particular vertex.
Yeah, coming to a vertex. Okay, and then you can do topological sorting or can calculate longest path. Right? Okay, if we have this type of yeah, go ahead.
Sir,
Sir,
the long.
With
Can
the
we discuss here the longest path calculation that's coming in week 11?
I can't hear you at all.
The longest path calculation using DAG.
The longest path can
A calculation how the longest path is incrementing based on the topological sorting. That is actually coming in the week 11. That's not discussed yet.
okay. So longest path in on the log DAG, right?
Yeah. Yes, sir.
Yeah, we'll start from there itself. So we'll start from here only. So I was just asking whether you are knowing the topological sorting or basic idea about the DAG or not. If you are, then we are ready to go. We'll start with the
Yeah. Yes, sir.
longest path. Okay. Okay. So what generally you do while doing the topological sorting? What are the steps that you follow? Can somebody tell me the steps? What is the first
Identify
step that you do?
in degree 0, the vertex with the in degree 0.
find
Remove.
all the vertex which have in degree 0.
Yeah, first you compute, right? the in degree for all the vertices. Correct? I is the vertices or vertices. For all the vertices, first you compute the in degree, correct?
Sir.
The second step is you pick that vertices which has in degree equals to 0, right?
Yeah.
Pick Vi equals to 0. What is the third step? You remove the vertices, remove that vertices, remove Vi and the edges connected to it, right?
Yeah.
Sir.
And somewhere you are noting down also. So the vertices you are noting down in a somewhere else, okay, whichever you are removing. And then again you are computing.
Degree with another
In degree.
Basically you are updating the value, correct?
Yes.
Sir.
In degree. And then you are again repeat from 2 to 5, correct? This is what you are doing basically
Sir.
in the topological sorting. Okay, so basically here also you'll be doing the similar thing, not the exact same, but there is one extra thing that we'll be doing here. So you'll be along with updating the in degree, you'll update a one other variable also. So here only you're updating only one variable. In the longest path in a diag, you'll be updating other variable that is longest path to the vertices I. Okay, this is what the difference is. So I'll just write it down the steps that should be following while calculating the longest path in a diag. Okay, and then with the example, with a very simple example, maybe a complex example, we'll try to do that. Okay, so the first step should be what? If you have read it, diag, what should be the first step? So in the first step is, again you have to do the same thing, compute in degree. For every vertices I in that diag. Okay, what is the second step should be for? I told you one more variable will come. You have to initialize
Longest path initialize.
One more variable, that is, yeah, longest path to
0.
To that vertices where the in degree is 0 for I belongs to. So you'll be initializing the longest path. Basically, you'll be initializing the longest path, like you'll be initializing the value. How do you do that? You just put it 0 for each and every vertices, right?
Yes.
For each vertex, there will be two values, one for in degree, another for the longest
Correct.
path.
Correct. You'll be having two values, one for in degree and one for that the new variable that we have updated now. Okay. The third step is, now you have to find a vertex u. So till now we have just initialized the value. Now you have to find a vertices u with in degree 0 and remove it from the DAG. What you'll be doing? So you'll add this value, add this whatever this u was to the topological sorting and give update and give the value longest path to u. So basically when you'll start, so you just selected a vertices with the in degree 0. Okay, and then you have added in the topological sorting, and in the lower part you'll be updating the value of the longest part to that vertices. So if you have started from some vertices, what should be the value of that longest path to that u? If you have started from some vertices in the starting where I was 0, I was 0 means the in degree was 0. Okay, so what should be the value for this longest path to you, this vertices?
The longest path value will be 0 only because
Yeah.
from here we have started.
Correct. So we have started from here. So the value of this will be 0 for this vertices, the starting vertices. Okay. This is what I was saying. And then what you will do is the fourth step. So you have initialized both the value and then you have find that vertices when degree 0, removed it, put it in the tab topological sorting and also uploading the value of the longest path to that vertices. Okay. What you will do next is similar to the topological sorting, you'll be updating the value. Update the value of in degree for all the vertices that are adjacent and the last step is what you'll update the value of what is the I here? I is okay. So what are the steps here? So I just wrote it down the step. Maybe with the example, it will be very clear to you to understand that. And then what is the longest part? So there is a basic formula that you should be using. The longest to calculate the longest path to that I is the basically whatever the vertices that you have removed, the adjacent to that vertices, whatever the vertices was there, you have to calculate the longest, update the basically you have to update the value of longest part to that I. Okay. So that the formula for
+1.
that. What is the formula?
Max +1.
Longer to I or 1 plus longest path to U. And now basically you have to repeat it. 3, 4, 5. Okay. So this is what your whole step is. Okay. Is this clear? Should I explain with the example? Maybe that will clarify your doubt.
Example, sir.
Yeah.
Can you just scroll a bit down? So got it.
So let's start with one example. How many vertices are there? How many edges are there?
Um,
7, sorry.
7.
Okay. So calculate the, now you have to calculate the integrity for each vertices. What is the integrity for this vertex?
0, 0 is 0, sir.
No, in degree for this vertex.
Which one,
For
sir?
0, it will
How
be
many
0 only.
for this?
3.
That is, which one, sir? 3?
For this it will be 2, right?
For
How many
3,
will be there for 2?
2, 2. Oh,
Two.
sorry.
Zero.
Sorry, sir. Yeah,
2 is 0.
in degree 0, sir.
3 it will be 2,
2.
right?
1,
2.
2, 2.
Coming edges, and again 2 that will initialize to that other thing, the longest path to that vertex is 0, right?
Yes, sir.
Okay. So what is the we
Sir?
have done the first, yeah.
For 1, how come it's 2?
Where's 2? Only 1 I wrote. Okay, yeah, it's incoming edges are 2, right? The first one and the second one.
Okay,
Got it?
got it.
Yeah. So where will you start? The first and second we have done. The third step is find a vertices u with integrity 0 and remove it from the tag. What you have to do is add that vertices to the topological sorting and give the longest path to u. So what should we do in the third step? The first, second we have done. The third step is what you have to select a vertices where the integrity is 0. Which is the vertices that with the integrity 0?
0 and 2. Oh, sorry. 2.
No,
2.
0 has a in
Okay,
degree.
okay.
This is the green color is the in degree. So the green is what? The green is in degree. And the pink or pink is the longest path to I. Okay.
Okay.
So the you have to select 2, correct?
2.
Yes.
If
Sir.
you are selecting 2, if you are selecting 2, so in the topological sorting, it will start with 2, and what you have to do is you have to remove. What you have to remove? 2
2
and the
2
adjacent edges, right?
edges.
Yeah, so you remove 2 and the edges, correct?
Yes.
What you will do is first you are adding topological sorting and give longest path to u. So what is the longest path to u? What is the longest path to 0? Sorry, 2.
It is 0. It is 0.
0, right?
Yes.
Now you have to do is you have to update the value, correct?
Sir.
Okay. You have to update the value. To remove 2 and the edges, correct?
Yes,
Sir.
sir.
I have removed the 2 and the edges. Now we have to update the value of integrity for each of the values, correct? So you'll
Sir.
update the value of integrity. What should be the value now?
0 it will be 0
0,
and
0.
for 4 1.
It should be 0 for 0, correct?
Yes, sir.
For 1 it should be
0.
For
2.
1, it's 2.
1 it's 2.
For 3 it should be 2, and for
2
4 it
and
should be
4
1,
is 1.
correct? And if you have removed u means you have removed 2, right? So after if you have removed 2, what should be the I? Update the in degree for all the vertices that are adjacent to the vertex u. Update the longest path to I. Okay, and I is what the I are the adjacent to u. So whatever you removed in the previous step, so you removed, so u was 2, correct? So what are the adjacent vertices to 2? So the I should be what? 0 and 4, correct?
Yes, sir.
See, whatever
0
you're
and 4.
removing, so you in the third step, whatever is seen, so update the in degree. So first you have to calculate, see that where the in degree is 0. that remove that and add it in the topological sorting and update the longest path to that u. So that you have initialized 0. Okay, that was value 0 here, there. And now you have to do is update the integrity. You have to again update the value, but whatever you have done, so whatever the value that you have removed, store that I that are adjacent to that u that you have removed. Okay, so you have removed and I was 0, 4. So I is what? 0. Now, what is the value of u?
0.
2 that you have removed, correct? Now the longest part, you will update the value of the longest part.
Sir, I didn't get, sir. I equal
First,
to
you'll update for the 0. What?
Sir, how
Why I is equals to 0? Okay. Okay, I told you in the, so whichever vertices that you will remove, so
Yeah.
you have removed 2. So you just
Yes.
take a note of the edges that were connected to 2.
Okay,
So I told
two.
you now, update the longest path to I. And what is that I? I are the adjacent to u.
Adjacent to you. Okay.
So you are updating the in degree for all the vertices that are adjacent to u. Okay. And why I have written the adjacent to u is because this value only will change. Okay. Other than that, the other value will won't change. The in degree
Okay.
which were the adjacent, let's for example, for 2 it was connected, 0 and 4 was connected. So the in degree of 0 and 4 got updated. We
Okay.
have calculated for each and every vertices, but in any cases, this 2 will be constant because it was not connected to 2, right? If it is not connected to 2, that means that in degree for this vertices won't change.
Okay.
Correct? So we are just updating the value of all
0
the
and then
vertices. Yeah, what?
connected. All the vertices, this connected to 2. 2 means,
Yeah.
yeah.
So you are updating the in degree for that adjacent, and then I is the adjacent vertices that were connected to 2. So I is basically 0 and 4 for u equals to 2, right?
Okay, sir. Okay, sir.
Now you have to connect what you have to update the value something, right? You have to update the longest path to I, and I are adjacent to 2. So you have to update this value, right? Longest path to 0. And what is that value? I told you the formula. One formula I told you, right? This is the formula that you should be using. Maximum of longest path to I. So whatever the value is maximum, you should be writing that. So maximum of this or that, this. So longest path to I or longest path to 1 plus longest path to u. So the value should be what? Maximum of longest path to I. I is what? 0 plus longest.
Your voice is cracking.
Is what? 1 plus 0. So what is the 0 and 1? Correct?
Sir, your voice is breaking.
Did you get that?
Hello, sir.
Are you able to hear? Are you able to hear me now?
No, okay, sir. No,
So
okay,
is
sir.
the voice like breaking a lot or what?
So
Okay, should I change the device?
it's up to you. If you can take with this tablet also, there is no problem.
Okay, so I'll try once again. If it doesn't work, I'll change it to switch it to laptop. Okay.
Okay, sir.
Okay, sir.
Sir, your device has very low charge, sir.
Okay. Okay, I'll try to do it from here once, and then if it doesn't work, I'll change it. Okay. So I'll just repeat it again. So in the longest path in the DAG, what you have to do is first you have to compute the integrity for each vertices, and then initialize the longest path to each vertices, that is 0, and then find the vertices where the integrity is 0 and remove it from the DAG, add it to the topological sorting and give the longest path to you. Update the integrity for all the vertices, and then you have to update the integrity. Basically, you have to update for the adjacent vertices, but if you are updating for all the vertices, that is not going to make any difference, because only the adjacent vertices, the integrity will change. And then you have to update the longest path to I. Okay, and I is what? The adjacent to the U. See, I'm telling again, U is the vertices that has the integrity 0 in the previous step, and I is the adjacent vertices to that. Okay, so in this example, we have started with a basic simple graph, and then we have calculated the integrity for each vertices. The green number is the integrity for each vertices, and that we have calculated, and we have initialized the value of longest path to 2, and that initialization we have just keep it as 0 for each of the vertices. Okay, that longest path to that vertices. And what we have done is, now we have seen that where the integrity is 0. Okay, so for u equals to 2, the integrity was 0 in the first starting state. So we have added 2 to the topological sorting list and updated longest path to this 2 is 0, because starting from here only, so longest path to go to 2 is 0 itself. Okay,
Okay, sir.
and you can see that none of the path you are coming to 2, right? So there won't be any longest path to 2. So longest path to 2 will pakka be 0. Okay, and now we have removed the vertices 2 and the adjacent vertices like edges also. After removing, we came to see the graph got updated like this. Now what we have to do is we have to update the value of longest path to 0 and 4, because I was the adjacent vertices that is closer to 2. So u was 2, so we have got 0 and 4 as the I value. So we have to update the longest path to I, and that is for the longest path of 0 and longest path to 4. So now updating the value of longest path to 0, there is a formula that we use. Longest path to 0, comma 1 plus longest path to 2. And that we see the initialize in the starting itself, we have kept the value of longest path to 0 as 0, but 1 plus longest path to 2. Longest path to 2 is also 0, but the formula tells you 1 plus 0. So the maximum of 0 and 1 is what? 1. And you can see in the starting graph also, the longest path to 0 is what? From 2 to 0, right? So the longest path
Sure.
to 0 is what? 1, and that is from 2 to 0. Correct?
Sir.
Is it clear to everyone?
Sir, it is clear.
Okay. Now, what should be the third step? What should we do now? Okay, longest path to 4 also you have to calculate, right? And what should be that value?
Sir, now the longest
Longest
path
path
to
to
0 is 1, no, sir?
longest path to longest path to 0 is 1. Correct. In the starting it's 1, but we are updating the value, right? This is the starting value, but we are updating, right? After every step.
Okay, okay. No, in the diagram still the 0 is 0 only, sir. That's right.
Right.
No,
So
that you can update it, right?
Yeah.
Okay.
So you'll update it to 1, right?
Okay, sir.
Okay. And what
Okay.
should be the value for this longest path to 4?
1.
1.
1.
Okay. Now again, in the third step, you will be doing the same thing. sorry. Okay. Now you have to remove, what you have to remove? You have to remove the U. The earlier U was what? Now the U got updated, right? U is the 0 vertices.
So
And what is the I now?
0.
No, I. What is the I now?
I is
I
1.
is 1.
I now 2.
I
I
is 1.
is, what is the
One.
connected node to 0? 1 and 4, right?
Yes, sir.
Correct?
Yes.
Yeah. Or 3 is also connected.
4 is
right?
not
3 is
clearly
also-
visible.
3.
What?
3 also
The
connected.
4 is not clearly visible in the graph.
Is it not visible?
It is visible. You have to update the
Okay. Yes.
longest
Yes,
path
visible.
to 4 also.
Yes. Visible.
Okay,
Hello.
fine. Now the value of I is
Yes,
what?
sir, okay.
I, which is connected to 0, is what? I is equals to 1, 3, 4, right?
1, 2, 3. 1,
Okay.
3, 4.
Yes.
Yeah.
Huh. And what you'll be removing? You'll be removing something, right? The next
0.
step. You'll be
Edges, sir.
removing 0
Hmm.
and all the edges connected to 0, right?
edges of 0.
Correct? Until
Yes.
now, the topology, the list has been, the list is what? So in the starting we remove 0 and then 2. Sorry, in the starting we remove 2 and then 0, correct? The topological sorting list also we have to update,
Yes.
right?
Yes, sir.
And what is the longest path to that value? 2,
0,
it was
comma
0,
0 and 1.
0, 1. This is clear to everyone? Or are we
Sir,
writing this?
Sir, am I audible?
Yes.
Yeah, you're audible.
Sir, why we did not update the longest path of 4?
See, we have updated, okay, that is, but again we'll see that later part from here also the 4 will come.
Okay, we have to update only one of the node, longest path of only one of the node, which was
No,
connected.
basically you have to update all the values, but later also you'll see that it will get updated again.
But
See, so either you're updating, that is fine, but you'll be not storing in that value, right? Because you'll be storing only those value that you are removing. So for topological sorting, 2 got removed and you wrote the, for 0 you removed and you updated the value. So till now the longest part 2 was 0 and longest part to 0 is 1, correct?
okay.
Now what is the I? Now again you'll be updating, the 4 will come here, right? Now you'll be updating what? So you don't have to update the value of 1. Because you already updated the value 1.
Pardon, sir.
Yeah.
Value of 1.
So you have to
maybe-
update the value of 4 if, yeah. Go ahead.
So it is getting confusing.
Okay. So where you are getting confused?
With the numbers. Actually, can we take different graph with ABCD something?
Huh?
Can we take different graph nodes ABCD?
ABCD. Okay. So
Yes, sir. As so far I understood that the longest path, we are updating the longest path of the removing vertex. We
correct,
connect.
correct. and we are updating the value.
Okay, sir.
Okay, so what was the connection?
A to D also, sir.
What is remaining?
A to D.
So what is the first step that you should be doing?
Calculate the integrity for each vertex.
Calculate the integrity that I wrote it here. So you can just read it from here. First, compute the integrity and then initialize longest path to I. Okay, so the both thing you should be doing here. So the integrity for A is what? 1.
One.
So in the red color, I'm writing the integrity. Red is for integrity. And I'll be writing green, that is for longest path to I. Now this is 2, this is 0, this is 2, this is 2. So integrity is updated. What is the longest path to each vertices? Initialize with 0, 0, 0, 0, 0. Now the first step is what? So the second step is done. The third step is what? What is the third step here?
To the vertex with
Find the
integrity
vertices
0.
with integrity 0. So this is the vertices with integrity 0. Okay, so we'll start with C. We'll write it here. Sorry, what is this? C. We'll start with C. And we have to update the longest path to this I, or U, or whatever you want to say, longest path to C, and that is 0 because the initialized value is 0. Right?
Yeah.
And now we'll delete this. Now we'll delete that vertices because we already wrote it in the top, this, whatever the thing that we are updating, that we have wrote down for C. Now we'll delete that vertices and the adjacent vertices also. So we'll delete these vertices, not adjacent vertices, the edges that is connected to C. So we'll delete this. Now again we have to update the integrity for the remaining vertices, or you can directly update the value, update the integrity values for those vertices only, those were directly connected to the vertices that we have removed. Okay, or if you are getting confused, just update the value for all the integrity, all the vertices. Okay, for after every step you update the value of integrity. So this B, for B and D which are not connected, the value will not change, right? Because there is no any other changes on this B and D. Only the changes on A and E, because A and E was connected to C. Right? So again we'll update the value. After you update the value, what is the value we'll getting? The integrity. For this it will be
0
0.
and 1.
0. 0.
It will be 0. And for this 2, it will be 1. Correct?
Yes, sir.
But we have to update something, right? We have to update the value because
Longest
U
path.
was C. So you have to update, you have to update that value, right? What was this connected to C? The C was connected to A and E. So that is I is basically the adjacent to C and E. C. So whichever you have removed. So what is the adjacent one? A and E.
Okay, sir.
Now calculate the longest path to A and longest path to E.
Okay, sir.
What is this? Maximum of longest
Path to E, comma,
E.
maximum of longest path to the previous
1
one.
plus
Longest path to the previous one.
previous C. What is this? Max of 0, 1, and this is 1.
Sir.
Sir, this color
Right?
is not good, sir. Red is the color, sir. Red color is difficult to see, sir.
Okay. Similarly, you can update for longest path to E also. That will be, say it was A, right?
E. That is also 1.
Okay, this is 1.
Yeah.
Now what are you left with? This is what you are left with.
Yes, sir. So now we remove A. Right, sir?
Now you will remove A, correct. What are the values that you have updated? Tell me the values that you have updated till now. So you have updated for A, you have written what?
1.
1.
Longest
This is
path.
LPT. This is what you have updated. And again, for this also you have updated LPT as 1. Correct? Is this clear to everyone till now?
Correct, sir.
Sir.
But the condition that you are using to update the longest path, instead of that, can not we directly update the longest path, or simply say we can increment it by 1, because it is always going to increment by 1.
Yeah, you are correct. But see, later part you'll see that. So whatever you have said is correct. Totally, I agree with that. But okay, so we'll see that. Okay, and then we'll be able to know that.
Okay.
Okay. So now we have to remove what?
A.
You have to remove A, correct? So until now, what are the values that we have updated in the topological sorting? The first thing was what? C, and then
C.
A, and longest path to
A
C
and
is 0.
E.
This was the topological sorting that we have updated till now.
Yes, sir.
Sir.
E also, no?
No, E, we have, so whatever you are removing, you should be adding. So you have removed C, and now we are removing A. So that's why we have added A.
Okay.
Okay. So we'll
Okay.
remove this one. Now we'll remove this. And all the edges connected to A also. Okay. Now for that U, for U equals to, what was?
U was A.
Okay. And what was the I? That was connected to this U was all the three, right?
E, D
E.
and B.
All the three were connected to this, right? B, D, and E, right?
Yes.
All the three was connected. You can see from here, all the three were connected to A. So you just wrote I equals to, because I is the adjacent to that what you said that you're removing. You got this? Now you're updating the value. Now update the value for each of the I and A. So you'll update the value for first B. What is this? Max of LPT to B, comma, 1 plus.
LPT to A.
And what is this A?
Is 1.
So
One.
max of 0, 2 is what?
2, 2.
2, right?
2.
Similarly, you will be doing for LPT of D and LPT of E. So you'll be getting here max of what? LPT of D and LPT of 1 plus A. So what are the value you'll be getting here? Again 0, 2.
0,
That will be
Comma
getting
2.
2.
2.
And similarly, you'll be getting here max of, so you'll be getting again 2, right? Max of LPT of E, that was 1, 1 plus 1. So that is 1, 2 is 2. So you'll be getting, so you'll be updating the value of B, D, E, right?
Yes, sir.
But
So,
for
yeah.
D, it's LPT is 1, 0, right?
Right.
Obviously.
Yeah, in the starting it was 0, right? But 0, so LPT of, this is what? LPT of D, and this is 1 plus LPT of A, right?
Yes.
So LPT of D
yes.
was a 0, right? In the
Correct.
starting itself, we have updated to 0. We haven't updated the value of D, right?
Right.
Correct? But
Got
for E, we have
it, sir.
updated, right? In the previous step, we have updated the value LPT of that is 1. So this value was 1, right? The LPT of E was 1.
Right.
So this is 1, 2. That is 2. Similarly, for LPT of D, this is 0. And LPT of B, we haven't updated. So 0, 2. This is the 2. Right?
Correct. Got it, sir.
Okay. So now what should be added? We should be adding something right here.
Sir,
What is
E.
the value that should be adding?
We have to calculate first in degree of each one, right?
Yeah, correct. So in degree of, again, calculate the in degree for each vertices. The
For
in degree of B
E,
is what?
it's 0.
Degree of
D
D is
is
1, B is
it's,
1,
B
E is 0.
So what should be adding here?
E.
E should be added here.
Yes.
Yes, sir.
Yes.
And what should be the value for this? The longest part to E?
2.
What is the value?
2.
2, right?
2.
We have updated the value to 2. So it should be 2 here. And now we'll remove this also. We'll remove this.
Yes.
And what is the vertices that were connected to E? So for me now I is D, U was E, right? So that we have removed.
Yes.
And I is D. So LPT of D is what? LPT of D or 1 plus LPT
of E.
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 What is the value now?
2.
2, 3.
3.
3, yeah.
LPT of D, it will be 2.
2 plus 1.
Yeah, correct. So max of
2,
LPT
3.
of D is whatever the value it is, like it won't be maximum, right? This will be the maximum
1,
2. So you'll be getting 3, right?
Yes, sir.
Correct? So the updated value is 3 now. The LPT of D is 3 now. The updated value is 3. And now the in degree will calculate, you'll be getting 0 here and 1 here. So you'll be adding here. And what is the value you'll be getting? The longest path to
3.
D is 3, right?
Sir.
Correct? And now the remaining one is B. So now you can write it B. So did you get the idea how are we doing this?
Yes, sir.
Yes.
Is this clear to everyone? Is this clear or?
Longest path means we are adding the edges. No, previous all edges. No, sir. That is connected to that vertex. That node.
See, the two things you are doing, right? You are calculating in degree.
In degree,
two
I got
variables are there.
topological sorting. In degree, I understood, sir. This one.
So in degree you have understood. Then the other thing is you have to update. Every time you are doing the in degree, after that you are updating the value of longest path to that degree, that path. Okay.
Okay.
That vertices. See, you are calculate the in degree for each vertices, initializing the value for. See, if you will see the example here, you can see that in the topological setting that we have added to reach C, the longest path to reach C is 0. And why is that so? Because you can see that in the graph, in the main graph, where is that main graph?
Yeah.
That we have deleted. Okay,
This
let's see this itself. If you have to
Yeah.
reach 2 or C, okay, this is C also we have represented.
Okay.
And we have represented A here, B here, C, D, and E. So if you have to reach C, can you reach from anywhere C? Just check it. Can you reach it to C? Because there is no in degree, right? If you don't have any in degree, that means no vertices are coming towards you.
Yeah, correct, sir.
That means in the
No.
topological sorting, when you wrote C ka longest path is 0. That means you can't. So the longest path to go C is 0 only, because you can't go from anywhere to C, right?
Understood, sir.
Similarly, what was the next step? The 0, right? So, or A. And what was the
Okay.
value that we have updated? 1, right?
Yes, one path
And
that we
whatever
are.
he told was correct, right? Every time we are updating the value from 1 plus something we are doing, right? That
Yes, sir.
means if you have to reach A, what is the longest path? The longest path is this only, right? C
Yes,
to
sir.
A,
Yes, sir.
correct? Similarly, the next step is, what was the next? E, I guess, and the 2 was the thing. So again, from C to A to E.
Okay, another one. One more step. One more path. Okay, two,
Correct.
sir.
And similarly, the other step. So this is what basically we are doing with this all long form.
Okay, okay. Okay, sir.
You got the idea, right?
Yes, sir.
Okay. So I guess my tab will get off. I'll just join it from some other device. Okay. Are you able to hear me now?
Sir.
Yes, sir. Yes, sir.
Is this clear? The voice is clear?
Sir,
Yes,
it's
sir.
clear.
It's clear.
Okay. Okay. So this is clear, right? So longest path, how will you calculate, right?
Sir.
Yes, sir. It's clear.
So basically, those were like 3-4 steps that you have to repeat it till all the vertices you are adding to your topological, like whatever the sorting list, and from here you'll be getting the same sequence that you generally calculate in the topological sorting, because here also you are doing the same thing. You're just calculating in degree, wherever it's 0, you're just adding to the topological sorting. Only one more thing you are doing is you're updating the value of longest path to that vertices also. Okay.
Sir, one clarification I need. If I do like this, if I calculate the in degree of each vertex from remove by which have 0 each time, and add it to topological sorting, and below that where we were maintaining the longest path, I wrote down it like 0 1 2 3 4 5 6. Then it will also doing the same thing. If I do like this, then what will be the wrong in that?
No. See,
So it will not
if you
be in that manner. It may come as 0 1 1 2 2 3 to 4.
correct. This is what. Yeah. So in the topological sequence that you write doesn't always you're not getting the same sequence, right? If you're writing something A, B, C, if this is your topological sorting, that doesn't mean that in every next step you'll be reading the longest path. Like it can be
So,
something like that, right? The tree can be something different, right? Where the label is one itself, right?
so actually the max condition, the condition that we use to update the longest path, in the example that we have took, it was actually taking every time the maximum value, not the lower one.
Yeah, so if you have to calculate the shortest path, then you'll be taking the shortest, the minimum one. But see, there that example may be by mistake or whatever you want to say, you were getting 1 plus every time. But in that you already know that in the topological sorting, when you will do that sequence, you will write. That doesn't mean that A is being directly dependent to B in like next step. Okay, that is fine for this, but there may be some steps where the longest path can be 0, 1, and then 1 itself. It's not necessary that every time it will be updating to 2. Otherwise, there is no need of updating the value of longest path, right? Every time I would have
Right.
written like 1, 2, 3, 4, right?
So I have to take some other example and perform this algo on that. Then I will come to know where I'm missing it.
You can see the lecture. Sir has taken an example which is like that only.
Okay. So you can proceed with next topic.
Okay. So in the same example, whatever we took, if you have to reach, let's for example, what was, no, in that our example, every time it was increasing to 1. Okay. Yeah. It was getting increased every time.
Sir, in the lecture one, this graph is there, sir.
Okay. So let's start.
Activity 10.1, one question is there, sir. First question is there. Sorry, 11.1. 11.1.
Okay, we'll see that. So we'll first cover all the topics. Otherwise, it'll be like we've already took 1 hour for this algorithm, like the longest part.
Okay, sir.
So what is the remaining thing? So basically we have discussed 2-3 algorithms here, right? To calculate the shortest path also. So what are the algorithm that we have discussed in the lecture to calculate the?
You have to do transitive closure also.
Okay, that is like not that difficult. Okay, that will take some 2-3 minutes, 5 minutes max. For the next step, that the algorithm that we have read, what was the 3 algorithm that we have read here? What is the other one?
While
We will discuss these 2 today.
Hamilton is also there.
Okay, that is fine, but we'll discuss these 2 today, and I guess maybe Sunday we'll discuss the remaining portion.
Okay.
So the first one is what? Okay, so the transitive closure. So basically what is the transitive closure? Or matrix multiplication. Those both are simple, right? So you would have read in the CT also, right? If you have a adjacency matrix when given, adjacency matrix, if it's reflect for all Aij, where there is a direct connection from A to I to J, you will be writing one for in that whatever the matrix that you are plotting corresponding to some graph. Okay. And if you have to write A square, what does that mean?
A to K, K to J.
Yeah, you should be getting some K. Okay. So basically it's like pseudocode is like you should be getting some K in between I and J. So from I to J, it should be equals to 1, and J if I Aij is equals to 1 and sorry A K or Kj equals to 1, then you can directly put it AI. So this is what you do basically, and for A3 also you'll be doing the same thing. So with in A you have a direct connection, in A square you have what? You have a connection from you have like one with one hopping, with one hop, and this is for two hop, or you can write it like A square and this A, and basically their matrix multiplication step will come here. So it's not that difficult, and there won't be any like it's like not any difficult portion that it should be. Okay, let's for example you have a graph, simple graph. So what should be the graph? You have A, B, C, D, and E. Okay, so tell me this one. Okay, so if we have and the relation basically, what is transitive relation?
A is related to B and B is related to C, then A is related to C.
If A is related to B, is related to C, then
Is
A is
related to C.
correct. How will you write in the graph theory now?
We have
A is
to draw.
related to D and D is related to E.
Draw the graph from A to B and B to C, and then A to C.
Yeah.
If you have A to B, B to C,
To C.
right? Let's for example, this is A to B you have and B to C here, and if A to C is available, or
Yes.
let's for example, if you don't have C to, if you have in the adjacency matrix for this graph, simple graph, if G was the graph with the 3 vertices only, and this 2 vertices was not there. Okay, so whatever the adjacency matrix that you have plotted, A, B, C, A, B, C. So you'll be having what? AB you'll be having something, and BC also you'll be having. So BC you have something, and CA, okay, that is fine. CA is there. But if you have, this is what I was saying, if you have this matrices, this matrix, this adjacency matrix for this graph Z, whenever you'll update the graph Z dash for A square, that means now you're getting something. So with one hope, if there is a relation, then you will update the value for A square, right?
Correct.
So did you
Sir,
understand? Yeah,
Yeah, why the arrow is not A to C, sir?
No, see, in the CT you would have read something where if you have to update it, like if you have something like this, right? If A, I, K equals to 1
Okay.
and A, K equals to J equals to 1, then you can and this is and then you can directly write AI J equals to 1, right? See, This is the matrix for some graph. If you have been given some graph Z along with the adjacency matrix, correct, where you have a direct relation. So this is for direct relation. And if you have to update it for that one hopping, so what you will be checking for first, if you are going from A to B, and if you are getting something from B to C, then A to C you can go right with one hop. So what you will be doing in the graph, you will update the graph now. And now according to that graph, you will be having A square. That means with one hop, you will be reaching somewhere. So wherever you can reach it, like this, A to K and K to J. So you are getting some K in between from I to K, and then from, so then you can update from 8 IK also as 1, right? Because now you can reach it with one hop. Okay, this is what you are updating. And that thing you can do with the matrix multiplication also. How will you do? If you have A, so you can write it like this, right? Let's, for example, this is 4 cross 4 and this is also 4 cross 4. Okay, so you can do the multiplication, and the matrix multiplication happens like this. Okay, so whatever the, let's, for example, this is 1 0 0 1 and this is 1 1 0 0. Okay? So you'll update it like this. 1 into 1 plus. So if any one comes here, you can directly update it to 1 because there is some connection, right? What?
Mama,
Please mute.
Can you mute yourself? Okay. So see, what I was saying is, if you have a graph with adjacency matrix, and if you have to calculate for A square, that means like one hop also you want to include that, you can do it with the matrix multiplication also. Matrix multiplication generally happens if you have something like 4 cross 4. Basically here, whatever you are reading, every time it's a square matrix. But if you don't have a square matrix, something like this, 3 cross 4, and then if you have 3 cross 4, can you multiply this matrix multiplication? Can you do the matrix multiplication on this M1 and M2?
No, sir, because the one row is.
Yeah, because this should be, so the column of the first matrix should be equal to the row of the second matrix, okay, or the vice versa. Like, see, this one, the column, this includes the column, and this is the row for the second matrix. This should be equal. Then only you can do the matrix multiplication. Okay.
Okay.
Yes, sir.
Yeah.
Sir,
So you can update the value of A square, AQ, whatever, if you have a A. What?
sir, matrix multiplication is part of this week's lectures.
I guess it's there, right?
Sir, it is there.
Okay.
So you basically you calculate A square AQ. So with one hop, with two hop, with three hop, you can calculate directly with the help of matrix multiplication. Either you go to graph and then see that, check whether there's a connection with 2 hop, 3 hop or not. Directly you can do with the matrix multiplication also. This is what has been told in the lecture. Okay, this is the basic, just the example, like helpful method, matrix multiplication. And here, if you have something like this 1 0 0 1 and sorry 1 0 0 1 and then 1 0 0 1. So what should be the value, the updated value? So you'll do the matrix multiplication something like this. Okay, so some other values are I'm not writing. So what should be the value? 1 into 1 plus 0 plus 0 plus 1 into 1. So this is 2, right? So what should be writing? You should be writing 1 or 2 in A square.
2, sir.
No, see, this is what I told you in the starting. So whenever you have some matrix, let's for example, you have 0 1 1 0 and you are multiplying with 0 1 1 0. Okay, here so you'll be getting, you just write it 1 0.
Can you take in place of 1, 2, or 3?
What in place of?
In place of 1, sir, can you take or 2 or 3? Because 1 plus 1 square 1 square makes 1, it make confuse.
No. So this is not weighted now. This is not a weighted graph.
Actually, we are checking the edges are there, no? The path
Okay,
is present
see.
or not, no, sir.
If you have any graph G that is not weighted, if you have a non-weighted graph, in that graph, generally, whenever you construct the adjacency matrix corresponding to that graph, what do you write here? Tell me, if you have a 3 in this vertices, if you have A, B, and C, something like this. Okay. If you have this vertices A, B, and C, and here it is A, B, and C. What will you write? For A and A, you can't reach it to A. Okay, this is 0. So this all these 3 value will be 0. Now A to B. Is there any connection from A to B?
Yes, sir.
It's there, so you should be writing
One.
1 because this is not a weighted graph. In not non-weighted graph, generally, what do you write in the adjacency matrix? Is there any direct connection from A to B? If there is a direct connection from A to B, you can directly write it as 1. Okay. So
Yes,
this is
sir.
not a weighted graph. That's why I didn't took any weight. So you are just, this 1 replicates that there is a connection from this first row to second, like first vertices and the second vertices, whatever you want to write it, like A, B, C. And here it is A, B, C.
So we have what is weighted graph? Have we covered that?
Weighted graph we have covered, like we didn't cover, like it's there in the lecture, that we'll cover later. First we finish it this.
Okay. So right now, in the part that you are covering, in this we are not dealing with DAG.
So what is DAG? So we are working on the simple graph. This is basically a complete graph with non-cyclic. There should not, like acyclic.
But sir, the example you are taking in it is a cycle in that
There is a
cycle.
Discussed, now this is acyclic. This one is acyclic, sir. But one
Right.
you drawn before, as a result, we drawn 2 pages back, sir.
So where she had a doubt,
This one is cyclic, no, sir?
yeah, this is
It-
cyclic.
so her doubt was why we can't connect A to C. That is also possible. That's why it was looking cyclic. That's why I asked whether we are not dealing with DAG in this topic that you are covering.
No. So you can, so this will work on both the cases. So this, if you have something, so for any graph, I'm just telling, I didn't consider any particular graph. For any graph, you have this adjacency matrix. If you want to know regarding the A square, that means the connection, all the connection with 1 hop, you can directly do with matrix multiplication of AA. Okay, A basically is the direct connection, and this A is also the direct connection. If you multiply it, you'll be getting A square, right? And A square basically will tell you what? The connection with 1 hop, right?
Yes, sir. No, the question is why we are not marking the arrow A to C. Now the direction is C to A, no, sir.
So this was then, so this is the graph that we have took in the starting. It was something like this. We took in the starting, we got a graph something like this.
Okay, sir.
Okay, A to B, B to C, C to A. In the starting, it was there. So we didn't do anything, but just I told you, if you have A to B and B to C, so you'll be having A to C also, right? Because you can reach it from A to C, and that will be reflected in A square. So because you can reach it from A to C also with 1 hop.
Okay.
Correct?
Good, sir.
So this was given in the starting. So, and this is cyclic also, that is fine. But it just a normal graph, I took it. And then I just told you that this is a graph because there is a connection from A to C with 1 hop, that is B, with B hopping. So you can reach it from C also. And in the A square, that will reflect. So you can calculate it with the graph, or you can do it with multiply this multiplication, both A and A. You'll be getting the same. Okay. Should we move further to the weighted graph?
Yes, sir.
So
Yes.
what I've discussed till now, so this longest part got clear, right? Longest path. And this was not that the matrix multiplication, the transitive. So this is clear, right? The longest path to DAG and this matrix multiplication if you have to calculate for A square for the given A matrices for the direct connection, if you have to calculate for
Okay.
1 hop or 2 hop, you can calculate, right? The matrix multiplication. With the matrix multiplication, you will be able to get it. Correct?
Yes, sir.
Okay.
So,
So now
so,
we'll move to the weighted graph. Yeah.
so with the matrix multiplication, through matrix multiplication, we will get the shortest path.
No, not the shortest path. See, if you have a graph, right, corresponding to the graph, there will be some matrix, correct? The adjacency matrix.
Right.
And what does that adjacency matrix reflect you? If there is a connection from I to J,
Right.
it will be reflecting as 1 for the non-weighted one. Okay. And if you want to calculate A square, what does that A square mean?
It is a one hop.
Yeah, with 1 hop, right? So that you can calculate with A multiply with A, right? Or you
Right.
calculate directly from the graph. So you just see for, okay, there is a to B. So this is what I was telling. So if we have a graph A to B and B to C, then you can directly mark it as A to C also. For A to C, you should be marking 1 in this A square adjacency matrix, right?
Got this, but I'm not able to connect it with the practical application. What will be the use of this?
See, if you have some 5-6 train, right, or flight, okay, there is a connection that has been given already. Okay, can you reach it from A to C? If you have a flight from A to B and B to C, then you can reach it from A to B, C also, right?
Hmm.
Yes,
And
sir.
that will reflect in your A square with 1 hop matrix, correct?
Okay.
So this is what one
Okay.
application, but there can be a lot of application with this. See,
But
matrix multiplication can help you directly, right, to calculate. Okay, in spite of if you have a bigger graph like some 15, 16, so it's better to do with the matrix multiplication, right? If you have been asked to calculate for A5 or A6, A6 is like with 5 hop if you are able to reach somewhere, right? So how can you calculate directly? You can calculate A5 into A or maybe A4, A2
sir,
or maybe A3, A3.
sir, let's assume that I have calculated every hop that we got in the graph for A1, A2, A5, A6. Then what it represents actually? What is the purpose?
So I told you, no, it represents basically can you reach it from I to J with 1 hop or 2 hop or 3 hop?
Okay, we are just
Yeah,
counting the hops only.
correct.
So,
So
sir, in simple terms, if we say that if a graph is given and we draw the adjacency matrix of that graph, after that we do the matrix multiplications. Let's example A square. Then we get to know that from if there is an intermediate between them, can we go through that point or not?
yeah, correct. Is there any, so let's for example, if in the A square, 1A 1 3 is equals to 1, that means what? You can reach it with, you can reach it in A square if 1 2 1 3 is 1, that means what?
That means in
So there is an age
if
between 1 to 3. Yeah. So with the 1 hop, you can reach it here, right?
from the graph A, we can yeah.
So, okay, I am not able to hear you.
Yes,
Is
sir.
my
Yes,
voice
sir.
clear to everyone, or
Yes,
I'm
yes, sir.
having
Yes.
Your voice is clear. So with this, we are just calculating the jumps between two nodes.
see, whatever you said is correct. So you took the computational thinking you done, right? You have done that week 10.
Right.
Okay. So if you have any graph, this simple graph, I guess. Okay, take it like this one. A, B, C, D. Okay. What will be the adjacent matrix for this? This will be 0, 1, 1.
Except the principal diagonal, all values will be 1.
Principal 1 or
No,
0?
it will be 0. It will be symmetric.
Because we are not dealing with self loop, right?
Yeah, sorry, sir.
So for this matrix, for any graph G, the adjacency matrix when you are calculating, basically what you are doing, whenever there is a direct connection from some vertices I to J, you are directly writing it as 1, correct?
Yes, sir.
Correct.
This is what you are doing in the adjacency matrix, correct?
Yes, sir.
And if you have to ask, if you have been asked to calculate A square, basically A square denotes from any matrices I to J, you are finding a intermediate K. And if you are able to find an intermediate to reach J from I through K, then you can write it 1. Otherwise 0. This basically A square will denote.
Okay, sir.
See, if you are able to, if AI K is equals to 1, that means you can reach it from I to K. And if you are able to reach it from K to J, then denoted in A square, A equals to I to J as 1. Is this clear or what is the
Yes, sir.
doubt? Tell me what's the doubt here. Okay, try to. What's the point here? What's the big deal in understanding this?
Got it, sir.
No, if somebody doesn't got it, just tell me. I'll try to explain it again. Is this clear?
Sir.
Yeah.
Sir, I said that it's clear.
Okay. So now if you have a weighted graph, what is a weighted graph? What is a weighted graph?
Instead of, I think one, we are getting some other values as well.
Yeah, so there is something, so there is some weight for each age, right? If you have something, if you have to A to B, there is some weight been given, right? Okay, in spite of direct, you are saying that there is a direct connection. In spite of that, you are saying there is some distance or maybe some cost that is costing that. So some reaching cost or whatever you want to say. So this is what the your weight represents generally, or the time that you take to reach it B from A to B. Okay, so let's for example A at the stations, and then this edges denotes your time. Then you can, it's if somebody is reaching from A to, let's for example in this, can we do something? Okay, So if we were doing it in the direct graph, like where the weight was not represented, so to reach it from A to C, we were every time thinking that from going from A to B, let's for example, this all A are the stations and the edges are like basically a train that you're using. So from A to B, there is one train, and then B to C is the other train. So if you are reaching from A, so earlier, if there was only direct connection without a weight, you would have thought that it's better to go from A to B. Like it's better to go from what A. No, I did a mistake here. I guess it should be something so that the value should be lesser, 5, or maybe let's for example, this is 5. Okay. And 5 is, let's for example, the time you that you 5 hours you take it to reach from station A to B, and then 5 hours to reach from B to C. And if you are going from directly A to C, it's taking some 15 hours. So it's better to go by this way, right? A to B and then B to C, right?
So with this example, I'm getting like that it is showing the strength of edge between two nodes.
Correct.
Okay.
Yeah, and that strength can be anything. It can be time that it takes to reach here, or the cost it takes to reach from A to B. It can be anything.
And we are talking about cost. It means the lowest one will be better.
Yeah, correct. So in the
Okay.
weighted
Sir,
graph,
when we,
yeah.
sir, when we will draw the adjacency matrix of this graph, then we will reflect these values or one
No,
or
you'll be replacing, yeah, you're replacing the value of edge. So the whatever the value is there, the weight value will be replacing with 1. And wherever there is a 0, you should be writing 0 itself. Okay.
okay, okay,
For this
okay,
example, let's for example, this is A, B, C, D, and this A, B, C, D. So to A, okay, there is nothing. So A to B, what is the given here? 5, right? So you'll be writing A to B as 5. A to C, is there anything? Yeah, A to B is 15. A to D, is there anything? No. So it should be writing 0. Okay. So this way you'll be updating the adjacency matrix for the weighted graph.
okay, okay, okay.
Okay. And in this weighted graphs, there are different algorithms to calculate the shortest path. Okay. So it can be done in two ways, right? One way is to fix a point. So we fix one point and then calculate the distance, shortest distance to each path. Or the other one is to calculate for all points. For each and every point, you calculate the, let's for example, if you have A, B, C, D, then calculate A to C, B, then B to C. So all the other points you are calculating. So first we'll fix a one point and then calculate the shortest path from A to each other points. Okay. And there are like 2-3 algorithms that will be reading to do that. And those are like pretty simple. Those are like very simple algorithms that you will be reading here. So the weighted graph is clear to everyone.
Sure.
Yes.
Okay. So first that you will be reading, the algorithm that you will be reading. There's extra algorithm that this is the first algorithm that you should be reading. And this is basically to calculate, fix a one point and then calculate the shortest path. So yeah, basically this is a single source shortest path. Okay. So what you'll be doing here is like basically the example that with that what you can understand is like the example that the professor has given in the lectures is you have some different points. For example, you have 1, you have 2, you have 3. So basically you So you have to fix a single source, right? Let's, for example, for our one was a single source, the starting point. So basically from one point, you can think this algorithm as a, you are started burning something from here, okay? And the whatever you have burned, let's for example, there's a point A and you started burning. And the burning, so the time that it takes to go, that whatever you're burning, that it takes is like it is same in all the direction. Let's for example, after 1 minute, it is reaching here, like after 1 minute, 1 meter you can think as a 1 second. In 1 second, the fire reaches 1 meter. Okay. So if we have started burning from here, the first point 1. So after, so at this point, it is t equals to 0, right? At t equals to 20, where it should be reaching? It should be reaching at here, right? At t equals to 20 seconds. Let's, for example, this all are in the some meter. Distance is in meter, okay? At t equals to 20 seconds, it should be reaching here. So at t equals to 20 seconds, it will start burning this also. It will burn 2. So it has already burned at t equals to 0, 1. And at t equals to 20 seconds, it will burn 2 also. Right? And now if 2 is getting burned, so it will start, so the same thing will start from 2 also. It will start burning with the same speed, right? 1 meter, 1 in 1 second. Okay. So at t equals to 30, what will happen?
Burn 3.
3 will also get burned, right?
Yes.
Yes.
Correct?
Yes.
So at t equals to, so is there any better way to reach 2, right? There is no other, like the fire won't reach 2 before the 20 second, right? From anywhere. So there is only one path from 1 to 2, correct? And similarly, if you have to, the fire will reach at t equals like 3 at t equals to 30, right? At tal, so and at that time you can reach that at when the time was 20, the fire from 1 was all the direction it was equal, right? So it would have reached this direction, it would have reached half, right? The fire would have reached there. And again, after t equals to 10, like after 30 seconds, so here it was t equals to 20. And at 30, t equals to 30, it would have reached there, but it didn't reach there. So that's why from 1, if you have to, the shortest path to go 3 is what? This one, right?
Yeah.
Correct? Similarly, from 1 to 2, this is the shortest path, and you can see it from 1 to 3 also, this is the shortest path.
Okay.
But in the algorithm, how do you do? So this is the basic algorithm, but there you generally update some values. So there, how do you do is, you start with, so wherever your point is, source point, let's for example, the source point was 1, this is 1, 2, and 3. We have a connection 1 to 2 and 2 to 3, and there is a connection 1 to 3. That is 40, and this is 10, sorry, 20, and this is 10. So the starting point, you just start the value with 0. So at t equals to 0, this got burned. And now just put it as infinity, infinity for all the other cases. So let's, for example, you just updated something like this. With the graph, you can think of like a fire, and every time you'll be calculating the correct. There won't be any mistake. So, or you are doing with the algorithm, like you can write it like this, A, B, C. So we have started with A, so you are putting here it as 0, and other value you are putting just at infinity. Basically, the algorithm generally is if, so in the pseudocode, when you will write this algorithm, it is something like this. Then you will update the value. Okay, so the first example, so this is the algorithm basically that you are updating every time. Let's, for example, you start with 1. Okay. So for this, you have du as 0. You start with 1, your du is 0, plus the cost of reaching 2. So the cost of reaching 2 is what? 20?
Yeah.
Is this less than infinite? Because we have initialized the value in infinite, right?
Yes,
Yes, sir.
Okay, if this is less than infinite, then you'll update the value. So you'll update. So A to reach from A to B, earlier it was infinite. We have initialized all the value to infinite.
Yeah.
Okay. And if from here to reach here, if this is the weight is less than whatever the value it was there earlier, then you will update the value. So this is what du plus c, the cost of reaching from u to v is less than the cost of du, dv, whatever has been given earlier. This was infinity. If this is
Yes,
less than
sir.
that, then you'll update the value. So from here A to B, earlier it was infinite, and A to C, because this was the initialization point. Now from A, you 0 plus 20, that is less than infinite, so you'll update the value to 20. Can you reach A to C directly? What's the
No.
value?
40.
40.
40.
It should be 40, right?
Yeah.
Yes,
What
sir.
you will do in the next step is you'll take the minimum value. Okay.
Okay.
Okay, sir.
Now, whatever the minimum is there, now this is like whenever you do this circle, that means now you can't update the value of B. Because in this point, you have a minimum thing, so you will write it here A to B. So you got a shortest path between A to B, and that is 20. That is cost, or whatever you want to say, that the weight with weight 20. You can reach from A to B with weight 20. And that value you can't update. So you'll be writing it again here. Okay, that is fine. And now from A to B, can you reach C? A to B, C, can you reach it?
Yes, sir.
Yes, sir.
Sure.
Right? And what is the cost?
30.
Now you have a
10.
20 for this. So now it becomes du. So du 20 plus CV is what? 10. Is this less than 40? Yes.
Yes.
So
Yes,
you'll
sir.
update the value. You'll update it to 30. And now this has been already relaxed. Now you'll relax this. Now you have 30. So you'll write it down, ABC. And this is the 30 is the cost to reach from A to C. Okay?
Mm.
Okay, so I'll give you one example. Just do it for that example. You have some 6. One, 2, 3, 4, 5, 6. Okay. So there's a connection. 1. And the weight is something 9, 14, 9, 7, 15, 10, 11. Now calculate the shortest. How will you start? First tell me. And the starting point is 1. You start from here. So you'll write. Your starting point is 1. The rest point is 1, 2, 3, 4, 5, 6. Okay, you start with here 0, infinite, 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 infinite. Okay, now tell me what will you do?
1 to 2.
1 to 2, what is the distance? Now it is infinity. I told you you have to update by this plus cost of uv is less than infinite for this first case, then you will update the value. So 1 to 2, if you have to reach 1 to 2, so that is how much? 0 plus 7. Is that less than infinity? Yes.
Yes.
You'll update it here 7. Right? Similarly, 1 to 3. 1 to 3, if you have to reach from 1 to 3, what is the cost? 9. And that 9 is
9.
less than infinite. So you'll update it 9 here. Similarly, 1 to 4. Can you reach 1 to 4? No. So the value will be infinite itself. 1 to 5. Can you reach from 1 to 5? No. So that value will be infinite. Can you reach 1 to 6? Yeah. That is 0 plus 14 is less than infinite. So you'll update the value to 14.
14.
Now, which is the smallest one out of this? 7, right? So you are fixing the value. This value is fixed. Now it comes 1, 2. So the shortest path from 1 to 2 you have got. That is 7 with weight 7. Okay, so you'll be writing 7. So you'll not be doing anything with this. Now tell me, via 1, 2, can you reach 3? Is that any method that you can reach it there?
Yes, sir.
1, 2, 3 also you can reach, but that path is what, 17, right?
Yes, sir.
It's better to 9, 9 is better. So you'll be writing 9 here. Can you reach via 1, 2, 2?
Sir, I want to interrupt. So can you
Yeah, yeah.
take two edges with same weight, like 6 to 5 and 6 to 1? Then how it will go?
So you can choose any of the two.
So in that case, they on the same step, there will be two paths with same values. Then how we
Yeah,
will
got it. Like for example, if it was 7 here, so you would have chosen 2 or 3. Anything is fine. So you'll not be doing any mistake. You can choose any of the two.
Okay, we can proceed with any of.
You can proceed with any of the two.
And
Okay.
in the next one we have then one.
And then do the same thing. Do the same thing. You'll be getting, if you are getting the 7, like for example, 7, 7 in this, then on the next step, like for example, you have chosen 2 here. In the next step also, if it's 7, then choose this one. And because this is already fixed, I have done the circle, that means fixed. And that you can't update. That's why this algorithm is not used whenever you have a negative value. So this algorithm is only used when you have a positive weight. Whenever you have a negative weight, that means that this algorithm won't work, because we are fixing the value itself. Whenever we are starting with 1 to 2, and if this is a minimum in this first iteration, so we are fixing each iteration, we are fixing one value.
So my point
Okay.
is that in that case, can't we miss one path? We are going to the only one path.
Can't we?
Can't we miss the other path if they on particular step we encounter the same way? We will choose the one, either of one. Then the other one will, we will not follow that path. Because we are choosing only either of one.
If you are choosing, like for example, 2 also you are choosing 1 to 2, right? And if you
Maybe
are getting,
maybe the second path have shortest one to the other node.
okay, in this example, I guess it will come. So let's see this example. There will be one value where the number will be same. Okay. So in this example, there will be, I guess, the later part will be same. So you can see that from, I guess, if we'll make it 2, so to reach it 1 to 5, it will be 20, and then here also it will be 20, I guess. Okay. See for this example, I think so now it will be same for one case. 9 to 9 and 20, and then because you can see that to reach it 1 to 4 also it will be 20, 9 and 11. Okay. And to reach 5 also it will be 20, 9, 9, 2. Right? So it will be same for both, and then we'll see that what happens there. Okay. Okay. So now where were we? So from 1 to 2, can you reach 3? And what is the length? 9, right? And 1 to 4, what is that? 1 to 4. Can you reach it to 4 by a 1 to 1 to you can reach it by this, right? What is the value? 7 plus 15. So this less than infinite, so we'll be putting 22, right? So this is not circle now. For that example that I showed you, this is circle, but it's not circle. Okay. So then the first case we have circle 7, we have written 1, 2. So 1, 2 shortest path is fixed. Now we are remaining with 1, 2, 3 that we have written. 9 is the minimum cost or the shortest path with minimum weight. Now 1 to 4 is 22. 1 to 5. Can you reach to 5 by 1, 2? No. So it will be infinite here. Can you reach it to 6? Okay, that 6 will be all 14 itself. Now what is fixed? Which is the minimum one out of this 3? 4, 9. Correct? That
Yes,
means
sir.
1, 2, 3 is fixed now. So now we can reach it from 1 to 3 with 9 as a minimum weight.
Yes.
Correct? Now,
Yeah.
so this is fixed. So we'll just write it down here, and 9 is also fixed. Now we have to reach it to 4. So can we, with the help of 1, 2, 3, can we reach 4? 1, 3, 4. I told you 1, 3, 4 is 20. This is better than 20, right? So you can write it 20 here. So it's not circle.
Yes, sir. Yes, sir.
You can write it, right?
Yeah.
Okay. And using 1 to 5, 1 to 3, can you reach it to 5?
Sir, 1, 1, 2, 5. Yes, sir. 1, 2, 5 means
No,
1, 2.
using 1, 2, 3, can you reach to 5?
No,
1,
sir.
Sir.
you
No,
can't
no.
reach it, right? So it will be
No,
infinity.
sir.
Can you reach it to 6? That will be 14 itself. Or what? 14 or something else? Using 1, 2, 3.
1, 2, 3, 20.
Sir, using 3, we getting 2.
Correct.
17.
See this path. 9 plus 2. 11, right?
Yes.
This is better than 14.
Yes, sir.
So reaching 11. We'll be writing 11 here. What is the minimum now? Out of this 2, 11 is the minimum. So now you'll be fixing 1, 2, 3, 6. So now you can reach it from 1 to 6 with 11 as a weight, minimum weight, right? Now 7 is fixed, 9 is fixed, 11 is fixed. Can you reach it to 4 with the help of 1, 2, 3, 6? Sorry, 4 was already there. So what is the minimum cost to reach 4? So 20 was there. Is there any other way that you can reach it to 4? No, right?
No, sir.
No, sir.
Okay, so 20. Can you reach it to 5 now? Using 1, 2, 3, 6. So you can reach it, right?
Yeah.
Yes, sir.
So you can reach it via 14 and 9. What is 14 plus 9 is?
23.
23.
Okay. Is there any other way to reach it 5? Can reach it by this way, right? Okay.
Sir,
Wait,
9, 2, and 9. Sir, 1, 3, 6, 5.
So this weight is, what was the weight? I haven't given any weight for this. Let's, for example,
No.
6.
No, no.
So if you have to reach it to 5, how can you reach it? 5?
Sir, 1, 3, 6, 5.
1, 3,
6.
6, 5. Yeah. So this is the minimum, right? So 20 that I have told
Yes,
you.
sir.
Okay. Now you have 20, 20. What should you do now? Both are minimum, right? You can choose
Yes,
any
sir.
of the two. Just choose
Yes.
4. You have chosen 4 here. 1, 2, 3, 6, 4 now. So you can reach it from 1 to 4 with minimum weight as 20. Now we're using 1, 2, 3, 4, 6. Can reach it to 5. So these are all fixed. What is the minimum weight to reach 5? Now you have included 4. Can you reach it to 5? Can you reduce this weight 20? Now you're using 4. That means you have one more path. So you can reach it like this, but it's like more than 20. 11 plus 6 is 17 plus 9. It's like 26.
Yes, sir.
Okay. So it's this is the better one, right? So 20 itself. So now you'll do the circle and now you can reach it everywhere. 1, 2, 3, 6, 4, 5. So from 1 to 5, you can reach it with 20 as a minimum weight. Is it clear to everyone?
Yes, sir.
Yes, sir.
Is there any doubt? You can just ask me.
Sir, how we are fixing in 1, 2, 3? I mean, sir, I have understood.
Okay. So we are
But
fixing the minimum value that you understood, right?
yes, sir.
So see. So you started with 1. Okay. So you can, so this we are fixing 1 was the starting point.
Yes.
So whatever the value we are getting, the weight, whichever the minimum weight is there, that means what you can reach it from 1 to 2 with this minimum weight 7.
Then this vertex come left side.
Yeah. You can reach it from 1 to 2 with this only,
Okay.
this path. And this is the minimum path that you should be reaching.
Yes.
If you have to
Yes, sir.
calculate the shortest path from 1 to 2, that means this is the shortest path.
Yes.
Okay.
This is-
Similarly, if you have to
yes.
reach it from 1 to 3, then what is the weight? 9 should be the weight. There can
9
be
should
other
be the
path,
weight.
but this is the shortest path. Okay, and this is the only
Yes.
path.
Yes.
Okay.
Mhm.
So similarly, you can go from anywhere, from 1 to anywhere. Okay, with this shortest path, with this method.
And we are keeping the 1, 2, 3, 1, 2, 3, 6 in the left side so that we can recognize the
This
we
is
are
just
fixing.
written so that, see, if this was a directed graph, then this the pattern also would have mattered. But this is an undirected graph, right?
Yes, sir.
This for
This is
undirected, so this pattern doesn't matter. Only matter thing is you can use 1, 2 now to reach anywhere. You can use 1, 2, 3, all the 3 to reach anywhere. Just
Okay.
to know the weight. Okay, if this was a
Weight.
directed, then you would have started from 1 to 2 only. Right?
Yes, sir. Yes.
Okay, let's for example, you have other. So this, if you have understood, I'm just giving you a simple question. If you have, and then tell me if you have a negative 1, 2, 3. No, this. Can you use this method, this algorithm here? Will it work
No,
here?
sir. No, sir. Because this is negative.
Okay, this is negative, but will your
Can
algorithm
we
work?
give a try? Can we give a try?
Yeah, this is what I was saying. Can you work on this? So, okay, let's start with this A point. Let's A, B, and C. What should be the value? Infinite, infinite.
Yes.
The next step, A to B. What should be the value? A to B.
10.
A to B, it should be 10. A to C,
5.
5. So what is the minimum one? 5 is fixed. So this is fixed.
Yes.
5 is fixed now. Now AC you can use. A to C. Can you reach it to B now? What is the minimum cost to reach B from A? 10 only, right? Can you reach it in other way? A to B? No, right?
No, sir.
Can you reach it to A to C using now? No. Can you reach it to A to C in any other way?
No,
Oh,
sir.
sir.
Now
A
you
to-
can't.
Because
So
we-
5 is fixed. So now you can use A, C, B. All the 3 you can use. Okay. Now 10 is fixed. 5 is fixed. See, that's why I told you. So this in this algorithm, 5 is fixed, 10 is fixed. So if you have to reach it from A to C, B, you'll be taking 10 as a minimum weight. A to C is 5. Now if you update it again, so this is 10. Okay, that is fine. But if you have to use, if you are using A, C, B, all the 3, can you reach it to A to B in any other way? No.
No, sir.
Can you reach it to A to C using A, C, B, all the 3? Can you reach it? A, now you can reach it like this, right? Did you get the idea? See, you have fixed the value 5 and 10.
Okay.
Correct?
Yes.
Yes.
Yes, sir.
See, that's the demerit of this algorithm is this is fixing the value. If you have already fixed the value, that means you can reach from A to C via this shortest path only.
Okay.
And you can reach from A to B via this path only. But you can see that we can reach from A to C via this path with the 10 minus 8 means 2 weight only. But this algorithm is fixing the value. After one relaxation, it is fixing the value of this path. After second, it is fixing the value of this.
That means this method doesn't allow you to again go and update the value.
Okay.
Right?
Okay.
That's why in the negative, whenever
Sir,
you
but
have
if we reverse the arrow of A to C from C to A and then we proceed,
okay, come again. Okay,
if we,
I'll give you one more example. So this method you are like, you understood why we are not using this method, this algorithm.
because we are fixing.
Yeah, because we are fixing the value. After every one relaxation, we are fixing the value. After this, we have fixed the value of this 5. That means there is no other method that we can reach it to C via A. Okay, and only this method. This is the shortest path. Okay, and now from A to B, this is the shortest path. But now we can see that whenever you have a negative weight, okay, if you have a negative weight, -8, then you can see that you can reach it from A to C with 2 as a weight. But I'll give you one example
Yes,
with the
sir.
negative weight where you can use it, this method. Here you are not able to use, right?
Sir, but why we cannot use negatives?
Because see now,
Because
you can see,
because
you
we are
can
fixing.
use negative weight, but you can't use this method, this algorithm to calculate, to know the shortest path.
Okay.
This method, why? So that's why the other method generally comes into Bellman Ford algorithm that can handle the negative path also, because in that method you are iterating, you are updating the value n-1 times. If you have a vertices n, you are updating the value n-1 time. Here we are updating the value and fixing the value, right? If you are fixing the value, you can't update. This is what the algorithm tells.
Yes, sir. Yes, sir.
Right? After every relaxation, you are updating, you are fixing the value. If you are fixed the value, you can't update it later. That means you can't update it from A to C. A to C is fixed. A to C is
Now
fine.
got it, sir.
Can't update it. Now I'll give you one more example. Then tell me, can you use the like this algorithm or not? This is A. This is C, B, this C, and this is like this. Same 10, 5, -3. Can you use the same algorithm here?
So A to B 10, A to C 5, but we cannot go from A to C via B.
See, even you don't go, see, A to B, you started with infinite. A to C, what's the minimum weight from A to C? Is A to B is 10.
5.
A to C is what? 5. Now, so 5 you have fixed.
Fixed.
Okay. Now A to C you can use to reach B. B is 10 and this is 5. 5 is fixed. Okay. Now you can use A, C, B, all the 3. See, even you have fixed the value. Now, if you want to update it, let's for example, you want to reach it, you can see that either you follow this path also, you are getting 7, right? So whatever you have calculated is correct from this matrix. So even you have a negative value, but you are able to get the shortest path, right? Why you are able to get? Because this weight was, so in the above case, the weight was very high. Here it was very less. Even after updating also, you are getting the whatever you have calculated is correct, right? But don't use any. So if you have been given an example, can you use this method? You can use this method here, because this value, even though this is a negative value, is not affecting your shortest path, right?
Okay, sir.
Is it clear to everyone?
Yes, sir. Clear. So we can update the last value. I mean,
No,
A
you
to C.
can't update. I'm just telling, even if you are following A to C with via this is also costing you 7, right?
Yes, sir. Yes.
Sir, that is more than
This
5. Yeah.
method itself is like after every relaxation, after every step, you are updating one value, and that you can't change. That's why this method is not used for the negative feedback or what you can say negative weight. This example just I gave you if you have been asked in the exam, okay, with the help of that
Yes, sir,
this
got it.
method itself you have to, because this method, this negative value is not impacting. That's why you are able to use it, but you can't, you should not be using whenever you have a negative value. Because
Okay.
Yes.
the same thing, the benefit in the other algorithm that you'll be reading is that they are updating for each ages. Like if you have a 5 vertices, for 4 times it will be updating, right? So that's why updating each and every edges value every like n minus n 1 times, that will help you. Here we are not updating the value, we are just fixing. After updating, fix after every relaxation, we are fixing the value. Okay. Is this clear to
Okay.
everyone?
Yes, sir. Yes, sir.
Okay. So the remaining thing I'll be discussing on the Sunday session. So till now, whatever we have discussed, is this clear? If you have any doubts, you can just ask me.
Just
From the
one thing
starting
to ask.
question,
One thing
longest path. Yeah.
at
Go ahead.
the shortest path only. You can scroll down.
Yeah.
So the last, yeah, the last one, the last one.
Hmm.
One from B to C, it's -3, no?
Yeah, it is -3.
Sir, suppose if this had this graph been undirected, this is a directed graph. But if this graph had been undirected and we have started from B, then from B to C, the value would have come as -3.
So that's why you can't use this method.
Okay. Okay. Okay.
See, this example that I gave you, just to show you that even if you have some, like if your starting point is, if you were a starting point as B, then you start the value were what, -3. You are fixing the value as -3. But as you can't use for the negative cases, you should not be using this method algorithm. Okay, but if you are starting with B in the other method, then if it's come minus positive, that doesn't matter. Okay, so negative value doesn't only reflect any negative thing, it can be some positive thing also. Okay.
Sir, if the next method works for both positive and negative values, then why are we studying this one?
Because somebody was there who like who would have done this algorithm earlier, right? For the positive cases. So that's why we are doing.
Okay. Okay. Okay.
And then the negative, so that's why then the negative value came and this method was failing, so we came up with a different method. Okay, and then again that method will fail in some other cases, so there is some different algorithm. So this is what happens.
Okay, sir. Okay, sir.
But it is very simple to understand. Like if you have all the positive value, it will be very simple to calculate this method, even though
It's
the other
simple to
method
understand.
but this is the simplest one. Yeah. Okay, if you have any other doubt, you can just ask me, or else we'll meet in the next Sunday session.
No, sir, clear.
Clear.
Okay. Okay. Okay, then thanks everyone.
Thank you, sir.
Thank you,
Thank
sir.
you.
Thank you. Thank you very much.
Okay, thanks everyone.
Okay, sir. Bye, sir.